Principles of Momentum. 11th.1. Introduction. 7, 6, 5. We have go for main engine start. 2, 1, dot. We have liftoff. These words, spoken on April 12, 1981, marked the beginning of the first flight of the space shuttle Columbia. Thousands cheered as the Columbia blasted into space. Although the space shuttle was called a marvel of modern technology, it used the same principle as its predecessors, the early rockets, to get into space. That same principle also applies to such activities as playing marbles, target riflery, and bowling. The principle is the conservation of momentum. 11th.2. Definition of momentum. Momentum P is a measure of an object's inertia of motion. Isaac Newton called this property of an object its quantity of motion. For example, an object with large momentum, is harder to stop, than an object with small momentum. What physical properties do you think affect momentum? The first aspect of momentum should be obvious after a little thought. Which is easier to stop, a 10,000 kilogram truck moving at 50 kilometers per hour or a 0.05 kilogram tennis ball moving at the same speed? You can stop the tennis ball with one hand, but your whole body would not stop the truck. It seems clear that the mass of an object affects its momentum. Which is easier to stop, a 0.01 kilogram bullet moving at 1,000 meters per second or the same bullet moving at a speed of 1 meter per second? You can safely catch the slower bullet in your hand, but the faster bullet would cause great damage before it stops. So, an object's velocity also affects its momentum. It is not surprising, then, that momentum is defined as the product of mass and velocity. P equals mv, 11.1. Linear momentum is a vector in the same direction as the velocity vector. In the SI, mass is measured in kilogram, and velocity is measured in meters per second. Consequently, the unit of momentum is kilogram meter per second. The unit for momentum does not have a special name. 11.3. Changing momentum, constant mass. Since an object's mass is usually constant, a change in momentum is almost always a change in velocity. That is, an acceleration. Therefore, delta P equals delta mv, and delta P equals m delta v. Dividing both sides by the time for the change, delta t gives delta P over delta t equals m times delta v over delta t. But delta v over delta t equals a bar, so delta P over delta t equals m times a bar. Remember, Newton's second law is sigma F equals ma, so sigma F equals delta P over delta t, 11.3. In fact, equation 11.3 was how Newton originally stated his second law. A change in momentum results from an unbalanced force. An unbalanced force on an object changes its momentum. Does it make any difference how long the force acts? Consider a train starting from rest at a station. If its engine exerts a force to turn its wheels for 1 second, will its speed change significantly? Probably not. However, if its engine exerts a force for 1 minute, its speed, and therefore its momentum, will change substantially. By rearranging equation 11.3, it is easy to see the effect that the tire has on the change in momentum. Delta P equals sigma F delta R, 1.4. The longer the force is applied, delta T, the more the momentum changes. The product of a force and the time the force is exerted is called the impulse, I, of the force. I equals sigma F delta T, 11.5. By substituting equation 11.5 into equation 11.4, you can see that delta P equals I, 11.6. Although any force can be an impulse, we use the term impulsive force to refer to the forces on a system that are large compared to the other forces. When a ball fist dropped to the ground, gravity is the impulsive force. At the instant that a bat hits a ball, however, the force the bat exerts on the ball is the impulsive force, since lit is large compared to the force of gravity. The following example shows the importance of impulse. 11.5. Conservation of momentum. Firing a high-caliber rifle causes a powerful recoil. When a rifle fires, the exploding gunpowder exerts a force on the bullet. FRB for a time delta T. The bullet, therefore, exerts a reaction force of FBR on the rifle for the same time, delta T, according to Newton's third law. The impulse of the force on the bullet is IB equals FR minus B delta T. The impulse of the bullet on the rifle is IR equals FB minus R delta T equals negative FR minus B delta T. The change in the bullet's momentum is delta PB equals IB equals FR minus B delta T. The rifle's momentum also changes. Delta P equals IR equals FB minus R delta T. Delta PR equals negative. Delta PB. Delta PR plus delta PB equals 0 kilogram meters per second. The change in the rifle's momentum is observed as recoil. However, if the rifle and the bullet together are considered the system, the overall momentum of the SV stem does not change. This discussion reveals the principle of conservation of momentum. When no unbalanced external forces act on a system, the momentum of the system is conserved, stays the same. Notice that the momentum of the bullet and the momentum of the rifle both changed. However, they changed equally in opposite directions, so that the momentum change for the system was 0. Suppose a hunter with a rifle is stranded at the middle of a frozen, frictionless lake. How can he propel himself to the edge of the lake? Because there is no friction between his boots and the ice, he cannot walk. Suppose he fires the gun. The bullet is given momentum in one direction. Since no outside force is assumed to act on the rifle bullet system in the direction of motion, the rifle must gain momentum in the opposite direction to balance the bullet's gain in momentum. Of course, when the rifle moves, the man holding it must move too, since he is part of the rifle component of the system. Therefore, when the man fires the rifle, he moves in the direction opposite the bullet's direction. He will eventually reach the shore even if he fires only once. If he fires the gun repeatedly, he will reach the shore more quickly than if he fires only once. 11.6 Changing momentum. Variable mass. A space vehicle is in the same predicament as the hunter on frictionless ice. There's nothing against which it can push in order to move. The space vehicle's plight may be solved by a means similar to the hunter firing his gun. Instead of ejecting bullets, a chemical rocket exhausts burned rocket fuel, while an ion propulsion engine ejects charged particles. Such material is called propellant mass. As the propellant mass gains momentum in one direction, the spacecraft gains the same amount of momentum in the opposite direction. Therefore, engineers design the combustion chambers of space engines to rapidly eject as much mass as possible in order to develop maximum momentum. Let's examine how rocket propulsion in space works. Assume that the mass of propellant that is ejected as exhaust is delta m prop. The momentum of this propellant exhaust is the product delta m prop VXH, the exhaust velocity is measured relative to the rocket. If we assume that there are no external forces acting on the rocket propellant system, then the total change in momentum of the system must be 0. Therefore, the momentum of the rocket must change by an amount equal to the change of momentum of the propellant exhaust. The change of momentum of the rocket must then be delta PRX equals negative delta M prop VXH sex. If we divide both sides by the time, delta T, it takes to exhaust delta M prop of propellant, we obtain the impulsive force of the exhaust on the rocket. FXHX equals delta PRX over delta T equals negative delta M prop over delta T, VXHX. The term delta M prop per delta T is the rate of propellant mass flow, measured in kilograms per second. The impulsive force of the exhausted propellant, FXHX, is called thrust. Thrust is the force that accelerates the rocket. Expressing this equation in the form of Newton's second law, we get FXHX equals MRARX, or delta M prop over delta T, VXHX equals MRARX, 11.7, where M is the combined mass of the rocket and the remaining propellant within the rocket. Unlike previous examples, the spacecraft's mass continually changes as long as it ejects propellant mass in its exhaust. The left side of equation 11.7 normally remains relatively constant until the propellant is gone. Therefore, on the right side of the equation, as the rocket's mass decreases with time, its acceleration must increase. This case of non-uniform acceleration requires more advanced mathematics to analyze the rocket's motion. You cannot use the three equations of motion for systems where mass and acceleration vary.